Hey everybody, my apologies for not being able to be with you on Tuesday. But that said, we don't have a whole lot that I wanted to go over, so I think a little asynchronous lesson is going to be enough to get us where we need to be. In all honesty, like I said, we're already ahead of schedule, and so the only thing I really wanted to do today was really go into margin of error and confidence intervals, and that keeps us ahead of schedule. And that gives us the opportunity on Thursday to start hypothesis testing, which puts us continually ahead of schedule and allows us to continue to have a pretty relaxed semester from this point forward, not going at a breakneck pace. So, I know that we left off talking about margin of error versus sampling error. If you recall, it is the case that there is never going to be a perfect sample. We are always trying to use a sample to understand the parameters of unknown parameters of a population. And so, given that we always know our sample is going to be imperfect, you're never going to get a sample that's exactly like the population. We know that there is a sampling error. And the sampling error is that difference between the sample and the population. Now, given that we don't know the parameters of the population, we don't know the true sampling error either, because you would have to know what the sample looks like to know how far off your sample. You'd have to know what the population looks like to know how far off your sample is. And so we can do a statistical process to find margin of error, which the margin of error is our best estimate of what the actual sampling error is. Now, margin of error is just an estimate, the same way a sample is just an estimate of a population. But this is the best we can do, and quite frankly, we can do pretty well and get a lot of really good information, even if it's the case that we can't 100% say what our true population parameters are or what the sampling error is. So, in order to get margin of error, that starts with something called standard error. So I'm going to talk about standard error, how to get that, which is really simple, and then how to get margin of error, which is even more simple, and then how to get confidence intervals, which is pretty simple as well. Now, I will tell you, all this math is really, really super simple. In all honesty, like, it does not take a lot of skill to do this math. It is necessary, though, to understand the inner nuts and bolts of how margin of error works and how confidence intervals work. So I want you to understand how to do this and understand the concepts that underlie it. That's the really, really important thing, because it's the case, like I said, the math is easy. The really, really important part is understanding the concepts that underlie it. So the starting point is standard error. Now, to get standard error, it's really, really easy. You just take the standard deviation and you divide that by n, the square root of n. And so you see, this is the formula. It's actually here twice. This is the symbol for population standard deviation. This is the symbol for a sample standard deviation. You're almost always going to see S rather than sigma because, like I said, we very rarely know the actual parameters of a population. And so if you have a standard deviation of 17 and an n of 5, you would take the square root of 5, and that is what you would divide 17 by, and that would give you a standard error of 7.6. So, like I said, that math is really, 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 really simple. And the next thing you do is you multiply that by the critical z-score of the level of confidence that you want. So if you remember, it's the case that when you give a confidence interval, you give it with a level of confidence. Your confidence interval is the window, the range that you are pretty sure that the true population parameter falls within. And so you give that with a level of confidence. So to give a confidence interval with a 95% level of confidence says that you have statistically figured out that there is a 95% chance that the population parameter is within that window. So, in order to get the margin of error, you find the critical z-score that is associated with the level of confidence that you want to use. I can tell you that it is generally either 90, 95, or 99. Now, you could use your z-score to actually find the critical z-value associated with the level of confidence that you want to use. And so I'll show you. This is not going to be necessary, but I'll show you how this relates to the z-table. But I'll tell you ahead of time that I'll just go ahead and give you the critical z-value for any level of confidence you may be using. In fact, there's only 3 you'll ever really use. So if you go to your z-table, let's say you want to find the critical z-score for a 95% level of confidence. So that means the critical z-score in which accounts for 95% of your total standard normal distribution. Remember, this all goes back to the normal distribution. So what you would do to find that is you would find the relevant z-score. And I'll tell you ahead of time that the relevant z-score for a 95% confidence interval is 1.96. And so if you go to 1.9 and then 6, that actually gets you to 0.975, which is 0.25 below 1. So you may be asking, why is it the case that a level that the z-score that's associated with 95% confidence actually accounts for 97.5% of the distribution? And the reason is when you are doing your level of confidence, it's 95% that you are correct within that window, but there's a 5% chance that you could be off on the low end, and a 5%, there is that 5% chance could be being off on either end. So there's a 2.5% chance you could be off on the low end, and there's a 2.5% chance that you could be off on the high end. And so that's why actually you get a z-score that you use the z-score, or the critical z-value rather, that is associated with 97.5% of the distribution, because it is the case that you actually, in order to add up to 5, have to account for the fact that you could be off, there's a 2.5% chance you could be off either high or low. So that's not terribly important. Like I said, you're always going to have the critical z-value. I just kind of wanted to show you why we use the critical z-values that we do. But in terms of what you're actually going to do, it's super easy. So if you are doing a 95% level of confidence, your critical z-value is going to be 1.96. If you do a 99% level of confidence, your critical z-value is going to be 2.58. So you just take the standard error that you just calculated and you multiply that times your critical z-score. And so if you want the margin of error on a 95% confidence, you just take your standard error and you multiply that times 1.96, and that's super easy. Remember, the reason why your z-scores are relevant here and you use a critical z-scores is because ultimately you are assuming a standard normal distribution. And you are, in order to speak with 95% confidence, you are saying that 95% of the total cases should fall within, or the possible cases should fall within this range that you are given. And so in terms of like actually doing the math, though, it's really simple. There's only 3 critical z-scores that you'll ever actually use, because there's really only 3 levels of confidence social science ever uses: 90%, 95%, and 99%. So the z-score for 90% is 1.65, 95% 1.96, 99% 2.58. And if I have you do this on a test, or when I have you do this on a test, I'll tell you straight up, I'll just give you a little table that tells you the critical z-scores for the levels of confidence. You won't even have to break out your z-table for this. So just a reminder, since this uses the empirical rule, it is necessary that you do this only with samples that are normally distributed. Because remember, we're using the z-table because we're assuming a normal distribution. And so you could do it with, for instance, player weight in the NHL hockey players' weights, because it tends to cluster around a mean of just over 200. And then there's a bell curve-ish kind of tapering outward from that mean. But if you do salary, that's skewed heavily upwards. Most NHL players you can see here make probably about $50,000 a year, which is not a lot. But there's quite a few outliers, like making $10 million, $8 million, $12 million a year. And so you could not calculate a confidence interval with that. In order to get standard error, margin error, and ultimately confidence intervals, you have to have data that is normally distributed. Now, the last step is the general formula for confidence intervals, which is super easy. Your standard error, your margin of error, which you've just already done, is signified by the letter E. And so your confidence interval is going to be your mean plus or minus E, your margin of error. And so this is the ultimate formula that combines both standard error here, and then this bit's the margin of error, including your critical z-score, and then take that plus or minus your mean, and that gives you your confidence interval. And these two equations are exactly the same. It's just one's sample standard deviation and one is population standard deviation. So let's go ahead and go over an example. So this is a normal distribution that I created using a random number generator. But just for sake of example, let's say this distribution represents a sample of 500 CNU students. And it shows the variable how many athletic events they go to in a given year. And so we have a pretty good sample, 500, which is about 1/10 of the overall student population at CNU. So it's a big sample. Our mean is suggests that most students attend about 4 and change athletic events a year. The sample standard deviation is 2.1, and our desired confidence level is 95%. So we are going to try and find a window that shows you, where our true population mean is for all 5,000 and change CNU students within 95% confidence. So in order to do that, this is how you go about doing that. This is just kind of a table I made to show you the individual steps, but I did actually do a recording of this to show you how it is done. So if you start off with your basic information, your sample is 500, your mean is 4.3, and the standard deviation is 2.1. And we know we want a confidence level of 95%. So start off with your standard error, 2.1 divided by the square root of our n, 500. Our square root of 500 is 22.36. So you divide 2.1 by 22.36. That gives us an exceedingly small number for standard error, 0.0939. And so be sure, if you're doing something like this, not to round too soon. Give it as many digits as you can, because as many of you found out, if you have really, really small numbers, rounding can oftentimes really, really screw things up if you have small numbers. So we've got our standard error of 0.0939. Now, the next thing that we're going to do is we're going to take that standard error and we're going to multiply that by our critical z-score. Let me move ahead. I actually recorded this earlier, but the audio didn't take, so I was annotating this as I went along. So we have a 95% confidence level that we're going for. So we know that our critical Z is going to be 1.96. So that's easy. You just have to look up what the critical Z is. I'll give you a table for that. So the next thing you're going to do is you're going to multiply 1.96 times your standard error. And that's really, really simple. That gives you a margin of error of 0.184. So we have our E now. Our margin of error, E, is 0.184. Now, all we have to do is do plus or minus our average in 0.184. And that gives us our window. Our window of numbers that we are 95% certain that our actual population parameter falls within. So that gives us a window that is between 4.12 and 4.48, with our mean right there in the center of 4.3. And so what that means is it is the case that we are 95% certain or in other words, there's a 19 out of 20 chance that the true population average of athletic events attended by CNU students in all of the university is between 4.12, so just over 4, and 4.48, so just under 4.5. So while it's the case that we'll never know the true population parameter, it still says a lot that we can take a sample and get a range of numbers that specific and say that there's a 95% chance that our actual answer is found within there. Now, one of the things you'll see is that, you'll notice is that's a really small window. Like, we managed to narrow our window down to like within half an event. That's really good. But the reason we're able to do that is because we had such a big sample size. Our sample size was 500. And so that is, once again, to emphasize why it is important that having a bigger sample size is always a good thing. You always want to have a bigger sample size rather than a smaller sample size. So that is how to do it on paper. This is a table of doing the exact same thing. This is your total, or your final equation for confidence intervals. And you see all the other equations are included. Standard error, and then margin of error, and then the full confidence interval. So, like I said, it is the case that I'll always give you a table that has the critical Z's. As much as probably the most complicated part of this lesson was me explaining to you, how to find the critical value on the Z table, you'll never actually need to do that. I'll always give you the critical Z. And so conceptually, what I think is really, really important for you to remember is the relationship that confidence and the width of the interval have to do with one another. If you have a higher level of confidence, or you want to use like a 99% level of confidence, you're going to have a bigger interval. So in our last example, if we used a 99% level of confidence, we'd probably have an interval that was probably like 3 to 5 events or something like that. I don't know exactly. I haven't done the math. But in order to speak with a greater level of confidence, you have a bigger window. Which is why, when you're trying to communicate statistics, it may not always be best to have the highest level of confidence, because you may have a window that's so big it's not terribly meaningful. So, for instance, if you're trying to say how fast people drive on Warwick in front of the university, and you get a sample of cars, and you get the average of 35, it may be more effective to say, I can say with a 95% confidence that it is between, the true population mean is between 30 and 40, than to say with 99% level of confidence, it's between 20 and 50. Oftentimes, it's more useful to give a smaller window, but also have a smaller level of confidence. The lower your level of confidence, the narrower your interval, the smaller your window. But ultimately, the thing that is the best case scenario is just to have a big sample size. Whenever you have a larger sample size, you're going to narrow your window. You're going to narrow that interval. Smaller sample sizes always give you a wider interval. So that's why larger sample sizes are universally better. So here is your review of symbols. Yeah, that's really all I wanted to do. I'll go ahead and tell you, like, right off the bat, we're going to do a problem like this when I see you on Thursday. And yeah, and that's how we'll start class, with a participation exercise doing this. And I will see you all on Thursday.